Combinatorial algorithms for market equilibria. Combinatorial polynomial time algorithms are presented for finding equilibrium prices and the allocations for the linear utilities case of the Fisher and the Arrow-Debreu models using the primordial schema and the auction-based approach respectively. An interesting feature of the first algorithm is that it finds an optimal solution to a non-linear convex program, the Eisenberg-Gale program. Resource allocation markets in Kelly's model are also discussed, and a strongly polynomial combinatorial algorithm is presented for one of them. Introduction. Thinkers and philosophers have pondered over the notions of markets and money through the ages. The credit for initiating formal mathematical modeling and the study of these notions is generally attributed to 19th century economist Leon Walras, 1874. The fact that Western economies are capitalistic had a lot to do with the overwhelming importance given to this study within mathematical economics. Essentially, our most critical decision-making is relegated to pricing mechanisms. They largely determine the relative prices of goods and services, ensure that the economy is efficient in that goods and services are made available to entities that produce items that are most in demand and ensure a stable operation of the economy. A central tenet in the pricing mechanisms is that prices be such that demand equals supply. That is, the economy should operate at equilibrium. It is not surprising, therefore, that perhaps the most celebrated theorem within a general equilibrium theory, the Arrow-Debreu theorem, establishes precisely the existence of such prices under a very general model of the economy. The first welfare theorem, which shows peer-to optimality of allocations obtained at equilibrium prices, provides important social justification for this theory. Although general equilibrium theory enjoyed the status of a crown jewel within mathematical economics, it suffers from a serious shortcoming other than a few isolated results, some of which were real gems, e.g. Eisenberg and Gale, 1959, and Scarf, 1973. It was essentially a non-algorithmic theory with the emergence of new markets on the Internet, which already form an important part of today's economy and are projected to grow considerably in the future, and the availability of massive computational power for running these markets in a distributed or centralized manner, the need for developing an algorithmic theory of markets and market equilibria is apparent. Such algorithms can also provide a valuable tool for understanding the repercussions of technological advances, new goods, or changes to the tax structure or on existing prices, production, and consumption. A good beginning has been made over the last 5 years within algorithmic game theory, starting with the work of Dane et al. 2002. However, consider the fact that markets were an active area of study for over a century within mathematical economics. It is safe to say that we have only scratched the surface of what should be a rich theory. Irvine Fisher C. Brainard and Scarf 2000 and Walras 1874 gave two fundamental market models that were studied extensively within mathematical economics. The later model is also called the exchange model or the Arrow-Debreu model, Arrow and Debreu, 1954. In this chapter, we will present the combinatorial algorithms for both these models for the case of linear utility functions. A second approach that has emerged for computing equilibria for these models is the solution of convex programs, since equilibrium allocations for both these models can be captured via convex programs. See Chapter 6 for this approach. Two techniques have been primarily used for obtaining combinatorial algorithms for these models: the primal dual schema, Vanner et al. 2002, and an auction-based approach, Gar and Kapoor 2004. We will present algorithms for the Fisher and the Arrow-Debreu models using the first and the second techniques respectively. An interesting aspect of the first algorithm was the extension of the primal dual schema for its usual setting of combinatorially solving either exactly or approximately linear programs to exactly solving a non-linear convex program. See section 5.5. The later program, due to Eisenberg and Gill 1959, captures equilibrium allocations for the linear case of Fisher's model. Unlike complementary slackness conditions for linear programs, which involve either primal or dual variables, but not both, KKT conditions for non-linear convex programs simultaneously involve both types of variables. The repercussions of this are apparent in the way the algorithm is structured. In a different context, that of modeling and understanding TCP's congestion control, Kelly 1997 defined a class of resource allocation markets and gave a convex program that captures equilibrium allocations for his model. Interestingly enough, Kelly's program has the same structure as the Eisenberg-Gill program, see also Chapter 22. The flow market is of special significance within this framework. It consists of a network with link capacities specified and source sink pairs of nodes, each with an initial endowment of money. Allocations in this market are flows from each source to the corresponding sink. The problem is to find equilibrium flows and prices of agencies in the context of TCP. The latter can be viewed as drop rates at links. Kelly's model attracted much theoretical study, partly with a view to designing next-generation protocols, continuous time algorithms, though not having polynomial running time, for finding equilibrium flows in the flow market were given by Kelly et al. 1998. See also Wang et al. 2005 for more recent work along these lines. Soon after the appearance of Vanner et al. 2002, Kelly and Verzirani 2002 observed that Kelly's model essentially generalizes Fisher's linear case and stated, continuous time algorithms similar to TCP are known, but insights from discrete algorithms may be provocative. With a view to answering this question, a systematic study of markets whose equilibrium are captured by Eisenberg-Gill-type programs was undertaken by Jen and Verzirani 2006. In section 5.14, we present from this paper a strongly polynomial algorithm for the special case of the flow market when there is one source and multiple sinks.